Good morning. Good morning in Cluj and good day in the other parts of the world. So, step by step, we are reaching the last day of the conference. Thank you for being with us, so many also in this keynote session. This first keynote part of the day will be presented by Lin Kayser. Lin is the CEO at Hypergenic Technology AG in Germany. And if we had in the first day a talk about disruptive innovation, today we'll talk about radical innovation in an age where engineering will be assisted by artificial intelligence. Just a few words about Lin. Lin Kayser is a German technology entrepreneur and inventor. He is the co-founder and CEO of Hypergenic, as I said, which is a software company pioneering artificial intelligence in the field of engineering for the future of manufacturing. Hypergenic's mission is to generate parts and entire machine completely computer algorithms and using the artificial intelligence. Since 2015, Hypergenic has collaborated with partners globally on the production of radically new forms of products. Lin's entrepreneurial journey stretches more than 25 years. He started his first company at the beginning of the 90s, and in 93 he joined startup Aradex to disrupt the world of industrial control system with PC technology. In 2000, he created his new company, Iridas. For a decade, Lin's team helped transform the global film industry from analog to digital through high-speed image processing technology. The company was acquired afterwards by Adobe in 2011. For 3 years, Lin held the position of Director of Engineering at Adobe, and afterwards, in 2014, left the Adobe to focus on his own ventures. Lin is a frequent speaker on the topics of entrepreneurship, sustainability, and the future of humanity. So, these are my introduction to Lin. Thank you, Lin, being with us today. We'll proceed like that. We'll give the floor to Lin, and he is handling the presentation. And yeah, good luck, and thanks once again for being with us today here in the conference.
Thank you, Stelian. Can you all hear me well?
Yes.
Great, fantastic. So yeah, thanks for this nice introduction, Stelian. I'm really looking forward to giving this keynote on this last day of this amazing conference. Like Stelian said, I've been around for a while. I've been now an entrepreneur for almost 30 years, and I've seen a lot of things. But today I want to talk to you about a topic that is very, very dear to my heart, and that is really, about actually, Stelian, I think, can you put my my video on full screen, because I will not be sharing any slides. The slides are behind me. Good. So I will talk to you about a topic that is very dear to my heart, and that is about innovation. Now, and by speaking about innovation, I'm kind of breaking my own rules, because I always say that the people who speak about innovation, they are very rarely the innovators, because innovators usually just do stuff, and then this is actually then just the innovation happening all by itself. So I'm breaking my own rule to talk about innovation, but I'm doing it for a good reason, because I think we are living in times where radical innovation is more needed than ever. And we have a lot of challenges, especially global challenges, that we need to overcome. I mean, this pandemic right now also kind of shows us, that out of the blue, things can happen that we didn't really think about. and that the world as we know it shouldn't be taken for granted. And I think this is maybe something that people have gotten a little bit too used to, that the world just operates as it is, and it is just happening, on a kind of predetermined route. And as all of us who are in technology know, this is not actually true. It is, we had a lot of really groundbreaking things that changed in the last couple of years, and we need a lot of groundbreaking things to change in the next coming years. And one of such a challenge is, for example, the climate crisis, right? This is a problem that we really brought onto ourselves. It is a problem that we ignored for a really long time. I mean, the first indications that the climate would be changed by the massive output of carbon emissions were already done in the at the end of the 19th century, so 1800 something. At least since the 1980s or so, we are pretty certain about what we're doing there. But we kind of chose to ignore it. And now we are in the 2020s, and we have to deal with it. So, there is things like that where we will have to radically innovate ourselves out of it. The time is kind of running out. And so we have to really make breakthroughs in engineering. And a lot of this involves machinery, right? So we saw a lot of innovation in virtual things like the internet and communications and these kinds of things. But we have not seen so much innovation in physical products. So if you look around you and look at all the physical products that you have in a room, around you, I mean, how much have these really fundamentally changed, with the exception of, these kinds of products, right? I mean, this has changed dramatically, and this is also kind of where it shows us what is possible. I mean, 10 years ago, basically nobody had this. It wasn't really invented. 20 years ago, very few people used the internet. It's very hard to imagine in a world where we have Google instantaneously at our fingertips, whenever we have a question. So 20 years ago, this didn't really exist. 30 years ago, very few people used PC technologies. And 40 years ago, basically all of this stuff wasn't invented yet. And I know this because I actually witnessed, the entire progress, during that time. And I will come to that in a second. But yeah, there is another reason why I'm kind of disappointed where we are today when it comes to innovation in most products around us and most objects around us. And that is, in the 1970s, my uncle, Lin Kayser, he started a really amazing company called OTRAC. It was the first first private company that built orbital launchers, so rockets that fly satellites into space. And his vision was, to make a cheap, not government-driven alternative to launching satellites into space. And, I grew up with this stuff. This stuff was all around me when I was a little kid. My grandmother, instead of having pictures of us grandchildren hanging on the wall, she had pictures of rocket launches, which I found cooler anyway. So, yeah, that was kind of my childhood. And there's a really nice movie. It's kind of, the trailer is playing in the background. My uncle, by the 1980s, he was launching rockets from his own private Cape Canaveral in Africa. And, filmmaker Oliver Schwem made a really, really nice documentary about it, which consists mostly of original footage from that time. So that was kind of how I grew up. And, for me, it was clear, by the time I've grown up, we would be flying into space, and, there would be flying cars and all of the stuff, that we read in science fictions about. Because, my uncle was doing it already, right? So he ultimately didn't succeed, not for technical reasons, but for political reasons. The time was simply not ripe for, especially a German company launching rockets in Africa. But still, I can't help but look back, over the last couple of years, a couple of decades, and be a little bit disappointed that almost none of this stuff really fundamentally has happened. And now it's starting to happen. Thank you, Elon. But it is a lot later than I thought. And so why? I mean, you can ask yourself. I mean, why should we actually think that innovation should be happening so much faster? I mean, isn't innovation just something that is driven by people, and it's slow, and things come along when they come along? It took a long time to go from a typewriter to a computer, and so maybe we just have to be patient. But I'm not patient because I witnessed this law here, Moore's law, right? Everybody here knows what Moore's law stands for. It stands for basically exponential growth in the computer industry. And if you look at what has happened in the last 40 years in the computer industry, you can go back further, but the last 40 years is something that I can talk about. It's amazing. I mean, 50, 60 years ago, computers were still these really big electromechanical devices. And today, everybody has a supercomputer in their pocket, and it's almost become like an extension of us. So, I mean, I don't know about you, but if I forget my cell phone, my smartphone at home, and notice it on my way to work, then I actually go back and fetch it. I mean, I can forget a lot of things: my wallet, my purse, my keys. A lot of things I can live without, but not my smartphone, right? So just within a couple of decades, it has become this part of us, that we use every day, and we are actually it's kind of a problem if you don't have this. And this has really not happened with any other object, if you think about it. Now, take a car, strip away all the plastic parts and all the decoration from a modern car, and it doesn't look that much different from a car in the 1990s. Now, again, Tesla is maybe the exception, and some of the modern electric cars coming out of Europe and China are also looking a little bit different, or actually radically different. So thank you, Elon, again. But if you take a gasoline car, it has surprisingly little innovation in it, even though it has evolved over 100 years now. Now, all the car people will now descend upon me and tell me, oh my God, you don't know what you're talking about. Hardware is hard. So it's really complicated to do hardware and machines, and so it just takes a while. So please don't be so impatient with us. It takes a while to add 10% improvement to a gasoline machine, and to a certain extent that is true. But still, I think it's incredibly unsatisfactory to give that answer. Especially if you think about what Moore's law is really about. Because Moore's law is not about software. Well, I get to that in a second. Moore's law is about hardware, right? It's a law about microchip. I mean, Gordon Moore was the co-founder of Intel, so it's not about software, and yeah, that's easy. It's about hardware. And microchips are fundamentally the most complex machines we humans have ever invented. If you think about it, microchips are the only human-built objects that actually approach the complexity of nature, of natural objects. You can argue that, in some areas, microchips are even more complex than natural objects, or at least they are very comparable. And that is quite amazing if you think about where microchips came from. So where did they come from, right? I mean, if you go back, if you dial back 100 years, computers looked like, had these mechanical devices. It was like calculation machines having lots of wheels and stuff. And they were amazing, but of course, they were very limited by the engineering that could go into it. Lots of parts, lots of engineering involved. Lots of work that went into them once you required a redesign. Some of the machines that Charles Babbage invented couldn't actually be built at that time. So he invented something that could only be built like 100 years later. So, and then, machines, calculation machines became a little bit more electric, and they became electromechanical. Some of you a little bit older still know the electromechanical calculators that you had in some of the shops. And then they became electronic, using vacuum tubes, and then the transistor was invented. And the transistor was a huge milestone because everything shrunk, dramatically. And that also sped up a lot of things because a lot of stuff was actually limited by the speed of light. But then came a big breakthrough, and that was the invention of the integrated circuit, the microchip. And the microchip allowed us for the first time to kind of print a computer. It's a process where you print a computer on a chip. And all of a sudden, you could kind of decouple the engineering aspect of the microchip from the actual production aspect. So both of these could evolve at the same time and evolve pretty quickly because they were kind of standardized. And the first microchips were obviously designed by hand. Some guy sat there and drew all the lines that made up the transistors and the capacitors and all of this stuff. And then, of course, they became computer-aided, the design tools, because before there were no computers, you couldn't have a computer-aided design tool. Now you had a computer. People could write software that helped you design these things by hand. But there was a huge crisis in the 1970s. I just told you that chip design and chip manufacturing were kind of decoupled. So chip manufacturing, using finer and finer structures, became so fast, the improvements became so fast, that was kind of what Moore's law postulated, that the guys designing these microchips couldn't keep up with their designs. And so in the 1970s, there was a very famous paper released by Xerox PARC, Palo Alto Research Campus, and it was written by Carver Mead and Lynn Conway. And they said, guys, we are doing this all wrong. We don't need computer-aided design. We need to do computer-generated design. So what is computer-generated design? So instead of a human sitting there and with the aid of a computer drawing something on screen, you actually put some of this thought process that the engineer does into a computer algorithm, and then the computer algorithm, with the knowledge of the manufacturing process, the chip manufacturing process, it actually creates these structures, the physical structures that make up the chip automatically. And that was a huge breakthrough, because all of a sudden, the speed at which you can engineer a microchip went through the roof. Because instead of designing something visually, you design something algorithmically. So in other words, you're creating an algorithm that designs something instead of designing it manually yourself. And this is what fueled Moore's law. So earlier on, I said, Moore's law is all about hardware, but to a certain extent, it is also about software, the software that actually helps with the design of the microchips. So why am I talking about microchips when we are talking about radical innovation? Well, first, it's a great example of what we humans are capable of once we find the right tools. But I think it is also a great example of what is happening in another field, in the field of engineering and manufacturing in general. So how do we currently engineer machines? We do it not that dissimilar to what Leonardo da Vinci did, or the Romans did. So here is a shot of a wonderful book I have here. It's a huge book, so otherwise I would have shown it to you, but it looks really clumsy when I do this because it's like this size and very thick. It's all the complete works of Leonardo da Vinci. And if you look at the stuff that he did, it looks surprisingly similar to a screenshot of a CAD program, that people use today to design machines. So how do people design machines today, and how did Leonardo da Vinci do it? They do it very similarly. So they imagine something in their heads, and then they sit in front of the computer today. Leonardo sat with pen and paper, and they draw it. And of course, today the tools are amazing. I mean, there's incredible tools out there that aid you, computer-aided design, CAD, that aid you in creation of physical objects. So with a lot of help, and of course it's all in 3D now, and it can run simulations and some automatisms and stuff like that. But fundamentally, it's still a very manual and laborious drawing process. And it is limited, first of all, by the time that the person has in front of the computer. And secondly, obviously, by the knowledge and the imagination of the people who are designing it. And this, I think, is one of the main reasons why manufacturing and the engineering of general objects, general machinery, is so much slower than what we are seeing in the computer industry. So that was kind of an epiphany I had a couple of years ago. And the epiphany was fueled by something else. And that's that I actually discovered industrial 3D printing. So 3D printing, I mean, everybody here knows 3D printing. I mean, when you think about 3D printing, you're usually thinking about cheap little plastic parts and Ultimakers and stuff like that. And it's all great. And there was a lot of hype around MakerBot and these kinds of companies, a couple of years ago, where they said, everybody can produce their little plastic toys in their homes now. And I never quite understood that vision. But I looked into 3D printing and I discovered industrial 3D printing. And the interesting thing about industrial 3D printing is that it has really, really evolved dramatically since its very first beginnings 30 years ago. So 3D printing has been around for 30 years now, but it has come such a long way. And today you can produce objects out of almost any materials. I mean, I see rocket engines being produced and aerospace parts being produced out of metal. I see filters being produced out of ceramics. I see people printing with living cells, which ultimately will become, organ replacements and skin replacements and things like that. I see people obviously working with polymers, but these polymers have come a long way. I see heat conducting polymers, stuff like that. So it's amazing. I mean, we've fundamentally encompassed all of the materials that we humans traditionally used for manufacturing, from glass to metals to, like I said, living cells, ceramics, everything. And I saw an analogy to the microchip industry, because I told you earlier that in the microchip industry, what we saw is that the manufacturing process became standardized and was kind of decoupled from engineering. And the thing about industrial 3D printing is, additive manufacturing, is that you can kind of decouple the design of the machinery that you're trying to build from the actual manufacturing process, because the printer has some characteristics, but fundamentally it doesn't care whether you print a rocket engine or a hip replacement, today. So they become kind of universal fabricators. You have to kind of decide on the process and the materials, but fundamentally they can produce anything that you feed it into. And so we see a similar decoupling of the manufacturing process from the design process that we saw in the microchip industry. And I saw that and I said, wow, this I think is going to be my next company idea. And I started a company called Hyperganic here in Munich. We work globally. We have employees on most continents of the world except for Antarctica. We work with amazing people all over the world, and our goal is to do exactly what I talked about earlier. Can we move Moore's law into the creation of physical objects? Can we get away from this manual, laborious process that hampers innovation because stuff just takes too long? So fundamentally, can we translate the thought process of engineers into computer algorithms and then apply them on a much higher level? So as an engineer, you become less of a solution provider and more like a question asker. So instead of coming up with a solution to a question, you become someone who asks extremely precise questions, and the computer can come up with the answer. And so what we're seeing here, I also have this object here, is for example, a relatively simple object for the stuff that we are doing. It's a bike helmet. And this bike helmet originated from the scan of a human head. And the interesting thing is it was completely computer generated, of course, but it also took into account the crash statistics of bicycle accidents. So if you look at the top here, you see that there's a lot of air coming through and it's very open. But if you look at the sides, it's closed. Why is it closed here? Well, this is where usually the impact hits when you have a bicycle accident. And the interesting thing is, because it's additively manufactured, every helmet can be different. And every helmet can take into account the latest information about the crash statistics. Of course, they can take into account your shape of the head. And I don't know about you. I mean, I've never had a fitting bike helmet. I have a big family, and every year I have to buy new bike helmets. It's one of the two most exhausting days of each year, because none of them fit. Everybody's head is different, and it's very hard to fit it into standardized sizes. So people try padding and all kinds of things. But what if you could just start with a scan of your head? And that's exactly what we did here. But as people, as the company, the bike company learns, how people actually fall when they hit their head, they can improve, the algorithms that actually create these objects. And the next helmet that goes off the production line will incorporate all of this. This is the power of designing stuff with algorithms. Now, there are also more radical things that you can do. For example, here, this is something we did almost 3 years ago now. It is a rocket combustion chamber. I also have it here. It was printed in metal, in Inconel 718, which is an aerospace nickel alloy. And well, it kind of looks a little bit like it is coming from outer space, like it was designed by an alien. And the reason is, it's actually true. It was not designed by a human. It was designed by a computer algorithm. And what we did here is we coded an algorithm that had all the knowledge about rocket combustion chamber design in it. And then we ran it and generated not one, but we generated hundreds and thousands and tens of thousands of iterations, and then ran them through physical simulation. And then we used genetic algorithms to actually find the best solution for that particular problem. So, well, you can also do that as a human if you're prepared to invest, I don't know how many 100,000 man hours to create 10,000 objects. But as a computer, you can just test out new stuff all day long, all night long, no weekends. You can massively parallelize this. You can run it on 100 servers if you want to. And so you can come up with really radical new objects. So there's a lot of stuff that you can do in optimization, using generative design, using genetic algorithms, using neural nets. You can learn what works. You can search only the parts of the solution space that actually sound promising, stuff that humans would do, but you can do it in a huge, on a huge scale using networked computers. And the objects that we generate now with our technology, they are awesome, really, in the truest sense of the word. You know, here is a feature detail from a chair we did the other day. I can't show you, the chair is not finished yet, and we're doing it with a famous designer, but it is really what you can do now. I mean, fundamentally, what we've created over the past 5 years is a technology that allows us to place atoms in space according to algorithms. So we can print anything that the 3D printer can output. We can model anything that the 3D printer can output, and we can come up with these crazy things. I mean, here is a vascular system. I mean, you know, one of the holy grails of additive manufacturing is, of course, using biologic materials. And, you know, really, I mean, I was so shocked when I heard this. So there are people working on synthetic livers and synthetic hearts using cells, and they actually design these things manually. So why would you design something like that manually? I mean, in nature, it's an algorithm. I mean, it's not like God sat on a cloud and designed your vascular system. I mean, it evolved through you know, millions of years of evolution. And today, you know, this blueprint, this algorithm, how to actually generate your vascular system, is encoded in your DNA. And that's basically fundamentally the model that we have to go to you know, in engineering. And so the objects that we generate, you know, start looking like natural objects. I mean, here's something that, you know, from microfluidics, you know, you can kind of see that things start to look a little bit more interesting. I mean, fundamentally, they start looking like the things you see here in the background. You know? It is actually surprising, even if you don't try to mimic nature, how similar to nature a lot of these things start to look like. Yeah? And the complexity that 3D printers can output is amazing. And one of the interesting things that we noticed is, as we move to AI-based design, things naturally start to become more complex. We humans always try to keep things simple. Yeah, we have like, we can only abstract so much. So we try to have like really sharp corner, we have parts, and they have very defined interfaces with screws and all of this stuff. Nature doesn't have that. You know, if you look at a tree and you think about it, it's really hard to tell, you know, where the branch stops and where the leaf begins. You know, it, you know, gradually changes. There's not, you know, some kind of screw hole and connector and a part that you assembled, you know, and this is true for all natural objects. And when you work with algorithmic design, where parts are not encoded as physical visual objects, but as algorithms that contain a functionality, things are automatically starting to become more complex and grow together. And, you know, in terms of complexity, I mean, here is something, this is actually a screenshot, you know, video recorded in one of our software tools. And you can kind of see, you know, that these objects start to become really crazy. You know, I will not tell you what this is, but you can kind of see that the complexity is really, really high. You know, and I will let it play in the background for a second where I'll talk about it. So why is complexity important? It is important because the most efficient and optimal things are often complex. That's the reason why nature out there is complex. I mean, if you look at a tree outside, it is the most optimal specimen for that particular place. You know, it grew to be perfect for that particular question that it was asked, you know, for producing basically carbon fiber out of atmospheric gases. You know, that's the job of a tree fundamentally, right? And it is extremely efficient in that, and it is efficient because it can actually handle, in terms of the manufacturing process of the tree, it can handle these incredibly complex objects. Now, here's another example. You know, this object here is a heat sink for a microchip. Now, if you look at it, it actually looks very similar to coral. Now, you could say, yeah, okay, Hyperganic actually used coral as the template, and they just created a coral algorithm. But what is the job of coral? The job of a coral is not to look like coral. A job of a coral is to maximize the surface area. And kind of the same thing is true for a microchip heat sink. It needs to maximize the surface area so it can radiate a lot of heat away from the chip. And so what we encoded is not a biomimicry of a coral. What we encoded is fundamentally just a way to maximize surface area. And well, there it looked like coral. Now I have a little bit more radical version because what we found is when we looked at this that it's actually not optimal, because contrary to coral, you also have to take the airflow into account. And so here is the new version. It looks even more radical. And this now is aerodynamically optimal. See that it funnels the air into the bottom of the heatsink to even maximize the amount of energy that can radiate away. So these are now these objects that can be computer generated and automatically created. And as I said, we now get to the level where we're talking about the same level as nature in terms of complexity. So our job really is to automate engineering. So what does that mean? It doesn't mean that you make an engineer superfluous. It's just that you move an engineer to a higher level. The automation we saw in microchips didn't do away with the people who design microchips. It's just enabled them to be incredibly efficient in what they are doing. And this is exactly what we are doing with Hyperganic. We're working with customers all over the world, from consumer goods to aerospace. And we find areas where we need radical innovation, and we find ways to speed it up radically. And there's a really interesting aspect about all of this, and I want to emphasize how important it is. So yes, of course, using algorithms, you can speed up things dramatically. But there is one additional aspect about computer-generated design that a lot of people forget, and that is communications. I mean, we humans are so incredibly successful compared to other animals because we can communicate. Now, there's other animals that can also communicate, but it's always verbal. I mean, there's actually some apes who teach their kids stuff, and they learn it from their parents. And so, actually, we humans did that also for a really long time. But then we humans invented a way to persistently capture information. I took this picture here of my office. I can't turn the camera around right now, but as you can see, I'm sorry for the mess, but I'm a book lover, right? I like books. And books are one of the most amazing inventions that we humans have ever created, because it allows us to persistently share knowledge, independent of the location, independent of the time. The person who wrote the book doesn't have to be there anymore, both in terms of time and in terms of place, in order for me to read it. And of course, we dramatically accelerated that in the decades using networking. So today, if I want to find an answer to something, I can just look it up on the internet. And there are databases and there are conferences like this one here, where we can exchange a lot of information. And it has dramatically accelerated things. But it still is a very slow process. So until I understand something, it takes a lot of time. Only because you speak Chinese doesn't automatically make me speak Chinese. If you know something about an invention that you created, it's not automatic that I can actually use it, even if you publish it. I will have to think about it, I have to learn it, I have to start to apply it. So it sometimes takes generations until good ideas catch on. Well, we don't have that time anymore. And that is, and what I find really encouraging is, because we are moving these inventions and this knowledge into computer algorithms, they are almost automatically networked, if we find the right mechanisms. And this is really important to me because we all need to work together on these solutions to our global challenges. You know, one of the things that I'm constantly always a little bit worried about in these times is now this idea also with the pandemic that we all, you know, should be doing everything ourselves, and we shouldn't talk to the Chinese, and we shouldn't talk to the Americans, and we only should be doing stuff in a European way, and then the Americans think the same way, and the Chinese starting to think the same way. And you know, how can we solve global problems if everybody thinks they have to be doing it all by themselves? And I think one of the reasons and one of the solutions to that is really networking and exchanging of ideas in an automatic way. If you, you know, talking about Tesla again, if a Tesla recognizes a new situation in traffic and finds a way to actually deal with it, all the other Teslas in the fleet automatically also realize how to work with this, because, you know, it's instantaneously distributed to all of the networked cars. And this is really something that we need to achieve with engineering. And I think we are on a good path now with algorithmic design and AI-based design. You know? Yeah. We are still mostly in stealth mode, you know, as a company. We are doing a lot of stuff I can't talk about. There will be more stuff I can talk about very soon. So, you know, I've showed you a couple of examples of what we are able to do. But I think it's a good time now to open the floor for questions now that I talked for 40 minutes as a monologue. So please, you know, any questions?
Yes, thank you very much, Lin. We'll have some questions, but first of all, please let me make have my thoughts about your presentation. Truly, I am very much pleased about this message of paradigm shift, and for trees community, this is my true belief. We all the time have to challenge even our algorithms, our way of doing things, to even seeing from a radical perspective the way we are creating something. And from this perspective, generically speaking, I think your talk is very much welcome in our conference. We have several questions. So one question was, and they are on the chat, but also I will invite the attendees to ask live the questions later on. But somebody said, what about the case of assemblies where you have more components to be assembled? And I assume that it's from the perspective of generative design, of course.
Yeah, that is an excellent question. I mean, I think parts are basically a way to get around the problem that we currently have with the distribution of innovative things. So, you know, we kind of distributed the problem of optimizing individual parts through by moving it into separate components, and then each of these components can be separately optimized. And you know, this paradigm actually works pretty well, and I don't see it going away anytime soon. But I think there will be a shift into integrated parts, you know, where instead of coming up with different parts and then trying to assemble it, you're coming up with different algorithms for different problems. And then these things then start communicating with each other to create a fully integrated component that incorporates all the functionality that you would usually put into multiple parts. But of course, you know, there will be, for many years, there will be hybrid workflows that will persist, and you know, parts are not going to go away anytime soon. But I see a shift from, you know, encapsulating functionality in a physical part to encapsulating functionality in an algorithm, and that algorithm can talk to other algorithms, and they can communicate with each other to come up with the best, perfect, you know, overall solution. You know, this is one of the things where I think we are going to see through. I mean, this is fundamentally that what nature does. You know, we are not assembled from multiple parts. You know, as humans, we are not assembled from multiple parts. You know, as a tree, you know, these are all components. You know, you can clearly see the differences, but you don't see where they actually interface because they're all, you know, gradually, you know, converge into each other.
Yeah, what's the idea of if we have some joints between the elements, they are naturally maybe generated also the joints to ensure the flexibility. Is right?
Yeah. Yeah.
Okay.
I mean, one of the challenges in the part system like we have today is that you never come up with an optimal solution. You always have to make a compromise because you basically say, okay, you know, I have this part and that part. I mean, think about an electric motor. You probably will not get exactly the one that you want unless you do a custom design. So you have to choose from, you know, the ones that are available to you. So you're usually over-engineering, you know, your object, and that means, you know, you're wasting energy, you're wasting material, etc. So it is, you know, this is one segue into a world where where stuff is globally optimized.
Great. There is a next question. You introduced actually that you have used and are using genetic algorithms and other type of generative design, but maybe because of the results of some of the objects you have shown us, somebody asked about the results just came from the algorithms, or you have introduced the concept of fractal geometry?
Actually, it's interesting because we did not teach the objects to have fractal geometry. So we didn't start with the idea of fractal geometry, but a lot of the stuff actually looks pretty fractal. And that is because, well, you know, the path finding algorithm through the solution space actually came up with stuff that looked fractal. And so, you know, this, it's a byproduct. It's not, I mean, one of the surprising things that we find is that a lot of the stuff that we do looks fractal, looks organic, but we never started with this. You know, we gave it just generic rules, and then it would just come up with these kinds of shapes. You know, we are usually as surprised as everybody when it comes to this.
Yeah, we have a next interesting question from Professor Hans Greb. Asking you about your position in relation with some theories, you know, the Kondratiev wave of technology. So over some period of time, something is happening again, and about the Schumpeter relative distractions theory and other paradigm changes. This is about the question, which is your position of this, let's say, cycles of coming something, destroying something, in putting something in place, or as in Kondratiev ways, long ways of even in inflation, when you see, or depression in the economics are very well known phenomenon. So maybe this is the perspective of engineering and engineering design.
Yeah, I mean, I think we see these cycles. You know, it's a good question of what is causing these cycles. I mean, like I said, you know, I grew up during the 80s and 90s, and you know, except for computer technology, it was a time of stagnation. You know, I mean, if you look at space technology, I mean, I shared with you my little story of my uncle. You know, in the 60s, 70s. There was a huge enthusiasm for that, and then you know, we went from being able to put people on the moon to back to basically being just sending people to low Earth orbit, and then you know, by the end of the 1990s, beginning of the 2000s, we had to use Russian rockets, you know, from the 1960s to actually send people to space. So you know, it clearly wasn't the high time of space technology, and you're kind of wondering why, you know, did it go from this enthusiasm and this really extremely fast acceleration of technology back to, you know, something where it was a lot of stagnation. You know, that caused a lot of frustration on my side. I think it's maybe people get over enthusiastic about topics and then they have to rediscover it. Maybe also people get a little bit comfortable with the current status quo, and it needs a little bit of a crisis to shake people awake. I think it's fundamentally a psychology thing and not really a technological thing. And that's one of the reasons why I think we need to move to a more technological solution to innovation than one that's just based on human psychology and human imagination, because that is what happened in the computer industry, and we're still seeing the results from it. Now, if you look at the computer industry closely, there's also certain stagnation there. I mean, there's not a lot of stuff actually fundamentally happening in many fields. So sometimes it needs a new field like quantum computing, for example, to come of age, exit research and give a new impression in gives a new impulse into this field. This is what we are seeing in rocketry now. I mean, sometimes it's also just a person, who gives an impulse, like with Elon Musk in the space and the electric car industries, But yeah, I mean, I think it's an interesting phenomenon. I don't certainly have an explanation for it. I'm just trying to solve some of the ramifications of it, because we are clearly running out of time with some of the global challenges. And if we don't speed up innovation, then we're gonna be in trouble.
Thank you, Lin. We have Yuri Borjani who has raised up the hand. So please, Yuri, ask the question.
Hello, and thank you for your inspiring keynote. So I'm pretty sure that the question I'm going to ask has been asked to you many times, but I cannot help myself. So we are facing global challenges, and while your solutions are all very, very customized, also for single people, you showed the example of the helmet. Do you think that this approach can become sustainable from the, of course, environmental, social, and economic point of view in the long term? And another question: what if what you help the computer design fails? I mean, is there any plan B? There are no replacements maybe in these integral structures that I love so much, but they might have issues. Thank you very much once again.
Yeah, thank you. These are great questions. Sustainability is one of the main reasons why I'm, behind this technology, because I think, our current manufacturing processes and also, the entire way we ship products and manufacture products in general is very wasteful. In terms of the manufacturing process itself. I mean, think about, most of you will probably be looking at laptops right now that are milled from a big block of stainless steel. If you think about how much energy goes into that, how much waste is created, it's insane. Additive manufacturing just places the material in the material that it absolutely needs at the right spot. And so it per se uses less material than traditionally manufactured objects. So this alone is a huge step forward. Then I talked about the standardization of manufacturing processes. If you design a microchip today, you can send it to almost any chip fab in the world, and it will be manufactured using a standardized process. So it doesn't really matter whether you produce it, in the United States or in Singapore and China. It will always be, manufactured to your specs and will be fine. So we are seeing a similar standardization in additive, which means that we can actually do away with a lot of the shipping, that we currently are doing with physical products. So this alone, should actually take care of a lot of environmental issues that we're seeing today. But then, of course, we have the ability to use novel materials. We're using additive manufacturing. You can change the material processes during the printing process. So you can use one material, for example, for an object that requires different material properties. So you can create an object that can be entirely recycled because it's one pure polymer object, even though it is maybe soft in one area and hard in a different area. This is something that people have never been able to do. So we, as humans, always use different materials and then glued and screwed things together. So this is also an aspect. But just generally, I mean, on a higher level, I think the ability to optimize objects on a global scale will help us transition to a pace where we can innovate so much quicker and actually solve a lot of the issues that we have to solve with technical approaches. I mean, there's a lot of talk about carbon sequestration, for example, getting carbon out of the atmosphere. Unfortunately, it's very hard because, funnily enough, there's not a lot of carbon in the atmosphere, so it's really hard to get stuff out there because you have to filter a lot of air, before you actually get a little bit of carbon. But some of these things can be solved, with really, really interesting filter systems and stuff like that. And here's an area where we see a lot of innovation. So I'm actually very positive that this acceleration of engineering innovation can actually help us out-innovate, some of the challenges that we have. Now, you spoke about some challenges when you talk about highly integrated objects, for example, that you don't have spare parts, that you can't replace one non-functioning part. So we have to be very careful that we're not creating a world where we're generating a lot of waste because everything needs to be thrown away. Honestly, I think the only solution, and that's fundamentally also a solution that will solve a lot of the current issues we have with recycling, is we need to come up with better ways of recycling. Recycling currently is downcycling because we are separating objects into their parts, and then we are trying to reuse the material from that part, almost directly again. Problem, of course, when you have polymers, when you have plastics, every time you heat them up, the polymer chains will degrade, will break up, and so you're always creating a lesser quality material once you have recycled something. So honestly, I think the recycling industry and the recycling technology need to evolve to a level where we are with nature, is that stuff is basically it is, we need to create the source materials again from the original, from the used materials, not, so in polymers, it would be going almost back to oil, and then creating new polymers from that instead of trying to reuse the existing polymer chains. So this is something, fundamentally that somebody needs to take care of, because otherwise we're not going to solve a lot of the issues. That is completely independent from additive manufacturing, but additive manufacturing is going to amplify it because, just like in nature, you will not be able to disassemble these things. I mean, yes, of course, you can design it to be disassembled, but a lot of the global optimizations will require that the stuff is fully integrated. And just like you don't take apart a microchip, you don't take apart a 3D printed electric motor because it's one thing, And so I see this problem, but I think it needs to be solved in a different way. And I think this solution will also help us, solve a lot of the other environmental issues that we have today.
Yeah, I think Yuri gave you a big yes. I think he's very much fan of sustainable development. I'm also on this side. Because of the time constraint, we have one last question, and this question will come from Professor Denis Cavalucci. Please, Denis, ask your question.
Thank you. Thank you very much. Good morning for those who are in the European time. But it's not the morning for everyone. First of all, I would like to thank you as a scientific chair of the conference. And I have two very short questions. The first one is very short. Have you heard about TRIZ before? Or does the word TRIZ mean something to you? Have you ever heard of it? And then I will have a second question after that.
I heard of it from Stelian, and I did not hear about it before. I'm not very well connected in the scientific community, I have to say. I've been an entrepreneur all my life, and so I've always been on the commercial side of things in a way, although I'm an inventor, right? So I have not heard about TRIZ before. Yeah.
Okay, great. So just to sum up in a half a sentence, we are pretty much interested in reaching or understanding what is the Pareto front of the possible optimization, but we are not really interested in optimizing. We are interested in disruption, in breakthrough, how to understand that there is a Pareto front, and then how to exceed this Pareto front and go towards an ideal solution, which will probably impose to find knowledge from outside the field where the problem is. So we are a professional and scientific community dedicated to that. What would a head of a company like you would expect from a scientific and professional community like ours? What could we produce for you?
Yeah,
in terms of new knowledge, how would we fill a gap that would be necessary for you in future by creating new knowledge?
Yeah, no, this is an excellent question. Now, how do I answer that in 1 minute?
I give you more. Yeah,
what is the most painful right now for you? And you would ask the scientific community to answer or make you theoretical proposals.
Yeah, I think the biggest challenge we have today is that a lot of the field of engineering is not very scientific. You know? So you have physics, yeah, obviously, and you have a lot of interesting things going on with applied sciences, of course, in engineering. But engineering itself is a very hands-on and practical field. And I think that's actually quite bad because we currently don't have models for how engineering works. You know, engineering is something that you do by looking at a machine and you know how it works, and then you design another machine just like it. But there is very little abstract knowledge about this. And there's a good reason for it, you know, because I mean, usually as an engineer, you have to be very careful about the production process. So you can't design something in an ivory tower and then hope to apply it. But if you look at, again, the microchip industry, it has a huge theoretical background, you know, also out of pure necessity because it has always been at the borderline of physics. I see mechanical engineering and engineering in general also moving in this direction. And I think there needs to be a spearheading effort with abstracting a lot of the knowledge and coming up with general rules, you know, from existing machinery about how this can be how this can be applied in a more generalized way. You know, really, you know, coming up with models, coming up with algorithms. I mean, a lot of the stuff is locked in the brains of engineers who've been doing stuff for like 20, 30 years. We need algorithms for that. And I think it's part of the responsibility of the scientific community to help with that abstraction, you know, just, you know, building a huge knowledge graph of especially mechanical engineering, because I see there is the biggest, problem. But also generally, I mean, there's this old joke, you know, if you have to add science, you know, to a field, then it's probably not science. You know, this is what people always joke about computer science, you know, and what people, of course, to a certain extent, joke about a lot of the other fields where engineers are working. And I think we have to move it to a more scientific level. Having said that, I think what is really important is that we create a better collaboration and interconnection between the people who actually apply the knowledge and the people who build the theories behind it. You know, this is one of my biggest gripes with the scientific community. Stuff is actually seems to be disconnected from the actual practical applications. And this is one of the reasons why we are not seeing enough progress right now in the solutions to these global challenges. You know, if we have...
I'm very glad of your answer. I'm very glad of your answer. Very glad, because this is the two heads of a tria, our community, you know, both professionals and academicals together in the same community on equal parts. And this is, you are drawing, in fact, the profile of our community. Thank you very much.
Yeah, I mean, this is, I think, the most important thing. I mean, if I can say one last sentence about this, one of my biggest worries today is that we are going away from a world of global collaboration to a world where everybody fights for their own. And I think the scientific community is one of the great examples where this is still not happening, fortunately. But we see it in the commercial world. You know, I mean, you see it with trade and all of these things. We have to make sure that we keep the global collaboration mechanism working. And I think the scientific community can play a huge role in that. And you know, if we can connect the scientific knowledge to the actual applications in a more faster and more aggressive way, and I think, you know, one of the ways is to move to more algorithmic design, then we can actually solve all these things. But without that, it's going to be really, you know, difficult.
Thank you very much, Lin, for very, very inspirational talk. Actually, I just like, and we'll end with this because we'll pass to the parallel sessions. Even the last message in your presentation about networking and instantaneous networking of adding new knowledge, I think that we have to take, as you said, global networking, but instantaneous transfer of knowledge in open innovation ecosystems would be something that will speed up the innovations in the world, and will make also this bridge between the scientific and the practitioner, the engineering areas. So thank you once again very much. We'll close here this keynote presentation, and yeah, I know that it's a very intriguing subject, but we can continue by communicating in different means, and maybe future collaboration will come also in this area. Thank you once again, Lin, and have a nice day, and have a nice weekend too.
Yeah, thank you so much for having me. You know, you can contact me at lin@hyperganic.com if you want to reach out. Okay. Take care, everyone. Bye. Have a great day.
Bye.